Welcome to another module of this NPTEL MOOCs course, Microwave Integrated Circuits. In this module, we are going to cover just a basic introduction of certain microwave components. Now, later on in the course, we will of course cover these components or various microwave components of different number of ports with somewhat detailed mathematical analysis. But in order to understand a flavor of this microwave engineering, let me show you some of the basic concepts behind these microwave components. So, the first thing that we need before going into this microwave components is the concept of modes in microwave engineering. Now, I have not given a solution or discussed about the solution of the Maxwell's equations for various microwave components. I just showed you the basic Maxwell's equation, the homogeneous equation necessary for solving for the electric and magnetic fields in the various microwave components. But there is something called modes, which we have to deal extensively when we are in microwave engineering. Modes are solutions of Maxwell's equation applied to a specific device. There are broadly classifying three modes. Three modes types, I can say. TEM, TE and TM. TEM modes are where both the electric and magnetic field are perpendicular to the direction of propagation. So, we have Ez is equal to Hz equal to 0, where Z corresponds to the direction of propagation. TE modes are where Hz is not equal to 0, Ez is equal to 0, and TM modes are where Ez is not equal to 0, but Hz is equal to 0. Now, not usually, it is always true that there is a single TEM solution. That is, we have only one electromagnetic wave which satisfies the TEM conditions. However, there are multiple TE and TM modes. Other interesting thing about these two modes is, in single conductor waveguides, only TE and TM modes exist. So, we are at low frequency like AC frequency, or when we are dealing with a DC battery, we are familiar with electrical power transfer only by means of two conductors. But then we have also electromagnetic power transfer to vacuum, where there are no conductors. Or then we have our microwave components, where single conductors, that is a single piece of metal, is able to conduct power. Now, obviously, we cannot have flow of charges as we know in conventional two wire circuits. So, here these single wire conductors, they simply act as a guide for the electromagnetic wave. So, there is no concept of voltage or current, there is only the concept of electric and magnetic fields. Whereas, the TEM solution is applicable only for two wire conductors. For example, say let us consider a coaxial waveguide. A coaxial waveguide can be drawn like this. And since we have two modes, therefore, TEM mode is the primary means of propagation. One other thing I forgot to tell you about this TE and TM modes, if I can go back to the previous slide, is that for TE and TM modes, they have something called a cutoff frequency. So, cutoff frequency is a frequency below which the TE and TM modes cannot transmit. For TEM mode, no cutoff frequency is there. So, they can transmit over any frequency. Now, the mode, as I said, for TEM and TM, there are multiple solutions possible, and that TE or TM mode for a particular waveguide which has the lowest cutoff frequency is called a dominant mode. Okay. So, then since in a coaxial waveguide TEM mode can exist, hence it can transmit over the entire range of frequencies. Hence, even though there might be some TE and TM solutions, TEM mode is the dominant mode. Now, an interesting example of a waveguide is what is known as a parallel plate waveguide. A parallel plate waveguide is a waveguide which has two parallel plates, and these plates are infinitely long and infinitely wide. The only finite dimension is the distance d separating the two plates. Now, the TEM wave solution for this parallel waveguide is given like this. The solutions for the TEM wave are given like this. Now, here Hx is oriented only along the x direction and E is oriented only along the y direction. E represents the electric field, H represents the magnetic field. Eta is given by square root of mu over E, is called the intrinsic impedance. That is the impedance due to the material properties. So, this is the TEM solution, and as we can see, there is only a single solution. We do not have multiple solutions. If we try to find out the other solutions, for example, the TM solutions, the solutions are given like this. The reason I am writing explicitly the solutions is because I want to show you some of the properties of these equations. See, the values of this electric and magnetic fields, first of all, H is oriented only along the x direction, that is perpendicular to the direction of propagation z, and E has components both along z and y. And note there is a variable n in these equations. What this variable n does is, for different values of n you get different solutions of Ez, Hx and Ey, and these various solutions for every new value of n are called the various modes. So, we do not have a single solution, we have multiple solutions, and then all of these will have a certain cutoff frequency, and the one that has the lowest cutoff frequency will be the dominant mode. So, we will have modes like say Tm1, Tm2, Tm0 and so on. Now, for a rectangular, similarly for a rectangular waveguide, there is a device called, or a component called a rectangular waveguide, which is just a hollow rectangular pipe like this. It is a pipe like structure with which is hollow inside, and the dominant mode for this is TE10. That is because whereas for the parallel plate waveguide we had solutions that varied only with a single variable n. In the case of this rectangular waveguide we have two variables m and n. So, we will get modes like TE10, TE11 and so on. So, TE10 is the dominant mode, that is it has the lowest cutoff frequency. So, for TE10 the field lines, if I can draw them, the magnetic fields are concentric like this, and the electric fields are like this. So, lambda by 2 separation will cause the electric fields and the magnetic fields to rotate in. So, the magnetic fields will rotate in opposite directions, and the electric fields, which are perpendicular to the direction of propagation, they will also be oriented in an opposite direction. Now, the consequence of this, if we can go back to this solution for the parallel plate waveguide. Now, we see that this propagation constant beta is given like this, where k is related to the actual wavelength that we see, and kc is a constant which depends on n and the value of d. D is the separation between the two plates. Now, this is for a parallel plate waveguide once again. Now, what you see is that this propagation constant beta, which is kind of the apparent wavelength that we observe, because beta is the spatial frequency in this equation. So, this expression will repeat itself after every beta value, after every lambda dash value given by 2 pi upon beta. So, if beta is the spatial frequency, but then the actual real wavelength that we have inputted into the waveguide is lambda. So, there is an apparent dichotomy or something, it is not matching. Usually, as you know, the frequency is related to the, as you know, the speed of, suppose c is the speed of light, then we have that is given by nu lambda, where nu is given by c upon lambda. So, like nu and lambda should be inversely proportional to each other, but by this relationship of beta is equal to k square minus kc square, where beta is the apparent wavelength and k is the real inputted wavelength related to the inputted wavelength, is given by this relationship. Now, this of course is related to the, is directly proportional to the frequency of input. So, then this simple relationship, simple inverse relationship that existed before does not exist anymore. This is the apparent wavelength, and this term is related to the frequency like this. So, if we actually plot, if you know, in fact, this equation is given like is actually given like this. So, we see that beta and omega are related by a complex equation. Of course, for high values of omega, beta is again proportional to omega. So, see 2 pi. So, initially the relation we were expecting was nu is equal to c upon lambda, or in other words 2 pi nu is equal to 2 pi c upon lambda. This implies omega is equal to beta c. So, here we had expected a linear relationship between omega and beta, but what we are actually observing is a relationship like this. Note that, as I said, for high values of omega the relationship will again be linear, but for low values of omega we get a kind of complex relationship, and if we plot this curve between beta and omega, then we get a curve like this. This is known as the dispersion diagram. Another component that is frequently and in fact most widely used in microwave engineering nowadays is the microstrip line. So, the microstrip line consists of a ground plane with a top layer metal with substrate with a substrate comprising of some dielectric like Teflon or glass epoxy or ceramic in between. This is the construction of a microstrip line. The problem with a microstrip line is that if we can come back to our written slides, the problem with a microstrip line is that it is, since it consists of two different conductors, two different dielectric materials, it is, even though it has two conductors, the modes are not strictly TEM. So, in a microstrip line you have a construction, if you take a cross section of a microstrip, which I showed in the previous slide, it is something like this, two metal layers sandwiched between some dielectric having a dielectric constant epsilon 1. If we had just air in between, then it would look something like this with all epsilon 0. Now, if air were there between, then it would be a true two conductor waveguide and TEM would be the dominant. But since it is not so, we have another dielectric material in between. What we usually do is we assume as if instead there is neither air nor the dielectric material present, but but this entire space outside and inside of this metal layers is covered with a material having a dielectric constant epsilon effective. Now, if suppose C is the capacitance between these two plates with just this dielectric present, and C0 is the capacitance between these two plates with air present, and C dash is the capacitance, say, with this effective dielectric material having epsilon effective present, then we can we can find out a relationship for this epsilon effective in terms of these measured values of C and C0. For example, so I was discussing the three types of three types of microstrip lines for analysis. One where there was a dielectric material epsilon 1, other where air was present between the lines, and the third where we had an effective dielectric material having dielectric constant epsilon effective present. Now, suppose capacitance C is the capacitance for this case, C0 is the capacitance for this case, and suppose with the effective dielectric constant epsilon effective also the net capacitance value that I obtain is like this, then I can write C upon epsilon effective is equal to C0 upon epsilon 0, from which I can write epsilon effective is equal to epsilon 0 C upon C0. So, this is the relationship for this dielectric constant, this imaginary dielectric constant that is surrounding the inside and outside of these metal plates, and it is related to the values of C and C0 with this relationship. Now, before ending this lecture, just one small concept I want to stress is the concept of impedance. Now, as you saw, we have single conductor waveguides for microwave propagation, but then there is no concept of voltage or current. Yet we inherently know that impedance, the concept of impedance is related to voltage and current. However, there is something called an impedance when we deal with various waveguides. So, the question is, what is this impedance that we are talking about? Since voltage and current are not effective concepts, we really cannot define impedance in terms of voltage and current always. We have already got a hint of something called intrinsic impedance, which is related to the property of the material, and that is given by mu upon epsilon. So, this is this is a value of an impedance which is purely dependent on the properties of the material. In addition, we also have something called electromagnetic impedance, which is the ratio of the electric to the magnetic field. So, here instead of voltage divided by current, we have Ex divided by Hy, and this is also an effective way of expressing impedance. In fact, for air, this intrinsic impedance comes out to be 377 ohms. That is why antennas, which are an interface, often considered an interface between air and a waveguide, the waveguide has to be basically designed to produce an impedance matching. The waveguide or the antenna has to be designed to produce an impedance matching of 377 ohms. Now, this is intrinsic impedance. For a microstrip line that we were discussing, we had found out what is an E effective, and for a microstrip line, the value of Z0 is often given by this formula, where epsilon effective, as we found, was equal to epsilon 0 C upon C0, where C is the measured capacitance between the plates of the actual microstrip line, and C0 is the capacitance between the microstrip metal plates had air been the dielectric medium. So, in this, so just to summarize this lecture, in this lecture we have covered some basic concepts about microwave engineering, like impedance, modes, dominant mode, TEM, TE and TM modes. and also introduced some of the devices that are commonly used in microwave engineering. We will of course cover other devices in more detail, but as a starting point, these concepts are very, it is very important to understand these concepts, like what is dominant mode, what is what are the TM, TE modes. And so with that we come to an end to this module. Thank you.